Today I am going to solve a problem on the stereochemistry of Diels Alder reaction. You can find this problem in CSIR NET exam 2015 December. Here is the problem. When this compound is heated at 150 degrees C, what is the product? The product, the options given here, it is very clear that the compound undergoes intramolecular Diels Alder reaction. The only difference in these compounds, it is the stereochemistry. There are three centers, 1, 2, 3. In that, what is the stereochemistry? In order to solve that, you should be able to view the transition state. I have given the transition state here. I have written the same molecule in this fashion so that it will be easy to understand. This is the diene and this is dienophile. I have placed one over the other so that they will react to give the product. Now look at that. This hydrogen and this hydrogen, they are going in the opposite direction. Since it is trans olefin, the dienophile is trans, so I have given like this. Even though there is no chiral center here, I have given in dotted line to show that it is going behind the plane of the paper. Same way, this one, it is coming above the plane of the paper. So when I make a bond between this, the two hydrogens will be trans. The same way, this hydrogen and this CO2Me, they are cis. So in the product, they should be cis. That means when they react, I get this product and the two hydrogens, this one and this one, they should be trans. And this hydrogen, that is this hydrogen and the CO2Me, they should be cis. So I should get a product like this. Now let us go to the given option. From the transition state, we understood that the two hydrogens should be trans. So in this, they are trans. So that is correct. But here it is cis. So not possible. Cis, not possible. Here it is trans. What about the stereochemistry between CO2Me and hydrogen? That should be cis. So in this it is cis. So this is the correct answer. In this it is trans. So this is also wrong. So answer, it is 1. I would like to discuss the important aspect of Diels Alder reaction. First one, it is Sisoid versus Transoid. The diene of Diels Alder reaction, it should be Sisoid conformer. That is, both the double bond should face the same direction. Cis doesn't mean that it is Z olefin. Since there is only one substituent, there is no question of E or Z. The Sisoid refers to both the alkenes, they are facing the same direction. Transoid, both the olefins, they are facing opposite directions. For a diene to undergo Diels Alder reaction, it should have this Sisoid conformation, or it should be able to attain Sisoid conformation by rotating through carbon-carbon single bond. For example, this one I can rotate through this bond by 180 degree to get the Sisoid conformer. Suppose if the compound is like this, still there is Sisoid conformation. But if it is locked like this, it is diene, 1,3 diene, but the rotation about this carbon single bond is not allowed. Because of that, I will not get Sisoid. So this compound will not undergo Diels Alder reaction. So the compound should have Sisoid conformation, or it should be able to attain Sisoid conformation by rotation about carbon single bond. That's why this cyclopentadiene is considered as a best diene for Diels Alder reaction, because it is Sisoid conformation. Here, what type of question may be asked? For example, I give this 3 diene, then the question may be, arrange the following in the increasing order of their reactivity towards Diels Alder reaction. Now, the second aspect, it is diene versus dienophile. Here, the diene whatever we use, it should be Sisoid conformer. In addition to that, it should be rich in electron. That means when I add electron donating group to this, like OMe, the reactivity increases. If I take methyl here, it's electron donating, but it is not as much as O, or that is methoxy group. So compared to this, the reactivity will be less. You may have come across this diene known as Danishevsky diene, where instead of OMe there is O-silane. Since these are electron donating group, the reactivity will be higher than other simple butadiene. What about dienophile? Dienophile should be electron deficient. That means if I add an electron withdrawing group, the rate of the reaction will be very high. So the electron withdrawing group whatever I add will be generally carbonyl compounds. So it may be aldehyde, ketone, ester, anhydride, etc. Or it may be nitro, maybe Cl. So these are some of the common electron withdrawing group that we use in Diels Alder reaction. So now, what are the other diene do we use in Diels Alder reaction? Most common one, it is furan. Here is the question. Furan acts as diene for Diels Alder reaction, but pyrrole doesn't. Why? Next compound, it is tetracyclone. This compound can act as diene. Next one, anthracene. This diene undergoes Diels Alder reaction. Another one, this kind of quinoid structures, they also undergo Diels Alder reaction. So these are very common diene in Diels Alder reaction. Third aspect, it is the product selectivity in Diels Alder reaction. There are three types of selectivity in Diels Alder reaction. The first one, it is regioselectivity. Second one, it is stereoselectivity. Third one, it is endoselectivity. Now let us go to the first one, that is regioselectivity. When I add a dienophile to a diene, here I get a compound like this. So there is no question about regioselectivity. But if I take a substituent in the diene, then there will be problem. For example, this will give a product like this, or the same thing, instead of placing the dienophile like this, I can place like this. I may end up with another product, that is by just changing the orientation of dienophile, I get two products. Which one will be formed? We can easily remember that 1,2 and 1,4 product is favored. 1,2. So this is the two substituents, they are in 1,2 position. So 1,2 product is favored, not 1,3. Suppose if the substituent is here, what I get is 1,3 product. But this product, since it is 1,3, it is not favored in Diels Alder reaction. Diels Alder reaction 1,2 and 1,4, that is these products are favored. 1,3 will not be formed at all. What is the reason? Even though you can easily remember as 1,2 and 1,4, what is the reason behind that? That is, I take this compound, now the lone pair of electron, it is in resonance, it is coming down, comes here, and this acts as nucleophile. The electron richness is more at this carbon, and it attacks the carbon which has less electron density. In dienophile alpha beta unsaturated system, this carbon has del plus, this carbon it has del minus. So this attacks here, this minus charge goes here. So what we get is a product like this. So that is 1,2 product. When we go for another one, if the substituent is here, this lone pair of electron comes down and this carbon becomes electron rich and this carbon is electron deficient. So a bond is formed first between this, then it attacks here. So what we get is 1,4 product. So easily you can remember 1,2 and 1,4 is more favored than 1,3. 1,3 will not be formed at all. The next one, it is endo versus exo selectivity. This selectivity is most common in when bicyclic compound is formed. That is, when I use this compound cyclopentadiene as diene and a dienophile, for example say this one, this acrolein, the product whatever I am going to get will be like this. So this is cyclopentadiene and this one it is from dienophile. Now the question is whether the CHO will be at the bottom or like this. So this is called endo, this one it is exo. Which one is more favored? Remember, endo is more favored because secondary orbital interaction. That is, there will be some kind of interaction between the carbonyl orbitals of carbonyl carbon and this orbital. Because of that, the endo product is more favored than the exo product. So you can see this is endo and this one is exo. So this CHO is inside the cavity of this bicyclic ring. So that is what we call endo. But here there is nothing like that. So this is called exo. Endo product is more favored because of secondary orbital interaction. It is stereochemistry. Third one, when a product is formed between this diene and a dienophile like this, product whatever we get has 4 chiral centers. Now, what will be the relation between this and this, which was trans earlier? What will be the relation between this and this, which was cis earlier? And what will be the relation between these two? So totally there are 3 possibilities, 3 questions. First one, what is the relation between these two groups substituent of diene, the product? What will be the relation between the substituent of dienophile, the product? And what will be the relation between the substituent of diene and dienophile? So there are 3 possibilities we are going to discuss now. First one, it is stereochemistry of substituents in the dienophile. To explain that, I make it simple. I go for a compound like this. Dimethyl fumarate. when it is subjected to Diels Alder reaction, the product whatever I get will be like this. Here and here there will be CO2Me. But what will be the stereochemistry? The stereochemistry, it is trans in the dienophile. So in the product also we get trans. Remember, this thin line and thick line, they are just to indicate the relative stereochemistry. Suppose if they are cis, like this, so dimethyl malate, what we get is cis stereochemistry. That is, the stereochemistry of the dienophile is retained in the product. Next one, what will be the stereochemistry of the substituent in the diene? That is, look at this. This olefin, it is E. This olefin, it is E. This I treat with, I take ethylene for simplicity. What will be the product? Here and here there will be methyl. Now the question is whether they will be cis or trans. You can easily remember, if both are E, you will get cis. If one is E and one is Z, so this is E and this is Z. In such case, I get trans. Remember, if both are E, we get cis. If one is E, another one is Z, then we get trans. Third one, it is what will be the relation between the substituent of diene and dienophile. To explain that, I have given the transition state. You can find the dienophile here. Since endo is more preferred, I have drawn in this fashion. And this is diene. And it is trans diene here. So, or it may be some alkyl group and here hydrogen. A bond is formed between this and this. So, you can clearly see in this transition state that this hydrogen and this hydrogen, they are trans. So in the product, whatever I get, if they are trans, then this also should be trans. So this or should be trans. On the other hand, if it is like this, so here it is Z olefin. This hydrogen and this hydrogen, they are in the same direction. So they are cis. Similarly, this also should be cis. Generally, they won't go for a diene and dienophile separately. Because in this reaction, I expect 4 isomers. They are stereoisomers, so it will be very difficult to predict which one will be the major product. That's why what they do, they go for intramolecular Diels Alder reaction where we get only two isomers which are enantiomers. So in the problem they are given intramolecular Diels Alder reaction that we get only two isomers which are enantiomers. Now let us go to the given problem.